Let's see, so A is the correct answer. Let's do a little bit of dimensional analysis. We'll have some other questions like this in just a bit, so I'm just sort of reviewing some of these things. Let's say that I have these variables, x, v, and a, and they have these particular units. X is measured in meters, v is measured in meters per second, and a is measured in meters per second squared. With that, what are the units of this expression? Let's say the expression is, oh, and then let's do t as well. T is in seconds. Let's say that I have a times t over x. A times t over x. What are the units of this expression? Are they meters per second? Inverse seconds, that's 1 over seconds. Meters squared per seconds cubed are just seconds. What are the proper units for that expression? A times t over x. Remember, when we're doing the dimensional analysis, we simply put in the units for each variable, and then we cancel out the things that cancel out. We simplify it. So you want to replace A with meters per second squared, T with seconds, and X with meters. Guys, when you're doing these clicker questions, you're welcome to talk to one another. So if you want to ask your neighbor what they got, that's perfectly fine. You can look at your notes. You can do whatever you want to do. You can call somebody on the telephone and say, hey, what do you think the answer is? All right, so you can talk with your neighbor if you like. And also remember with these clicker questions, you get credit if you get the answer wrong. You get twice the credit if you get the answer right. Right now, you know what? A lot of you have it wrong. A lot of you have the answer wrong. So if somebody tells you what they have, they probably have the wrong answer. In fact, there's a total of one person that has the right answer. Now 2 people have the right answer. Good. A lot of you have put D as the answer, and that's not correct. D is not the correct answer. Be careful with your fractions when you're doing this, how you deal with the fractions. We don't do a lot of math, but we'll do some simple algebra like this, or simple arithmetic. So as I said, D here is not the right answer. I'm going to help you out a little bit. So A is meters per second squared, T is seconds, and then X is meters. Whenever I encounter these, I would just like to write everything out in a string. So I would write meters per second squared like this, seconds, where seconds is in the numerator, and then I write 1 over meters. And then I go about canceling all the various variables. So if I do that, what am I left with? When I cancel out things in the numerator and things in the denominator, what am I left with? Okay, I'm just going to go about 5 more seconds. I'll stop at 3:20. I'm starting to hone in on the right answer. All right, B is correct. You'll have a couple of these on the exam, not on the reading quiz on Thursday. The reading quiz just covers chapter 1, but you will have 1 or 2 of these on the exam, which is coming up. I don't even know when it is. Anybody know the date for that exam? It's on your syllabus. You'll have it scratched it into your mind yet. When is it? The 24th of this month? Oh no, next month. Okay. 24th already passed. All right. So here, my meters cancel out completely, and then my seconds, one of these cancels out with one of these, so I'm left with 1 over seconds. So I understand why a lot of you put V, because we just had a seconds, right? But it was actually a seconds in the denominator, so it's going to be 1 over seconds. Okay? Not a lot of math in this course. We'll have some of this. It'll help you sort of as we go along to revisit, your basic, sort of 8th grade math, basic arithmetic and basic algebra. So, but I understand that, like in your other courses, you don't use a lot of math, and that's okay. And you're not going to use a lot in this class either. Is that correct? You don't use a lot of math in your other courses? What's that, Emily? That would be correct, yeah. And you won't in this course either, so I don't want to terrify you. All right. You can do that, yeah. So 1 over seconds is equivalent to seconds to the negative 1. Got it, and then some reason. Yeah, that's okay. I'll try to use simple fractions, not use exponents. But a negative number means that it's in the denominator. Okay. Does that answer your question? It is. That's the answer. All right. Let's do some more questions. So as we go through the class, I'll sometimes ask questions like this just sort of to see where you are. And then as we finish each sort of section, I have additional questions that I'll ask. I'll post these online with the solutions, but they'll make a good place for you to prepare for the exam. Sorry. Lost my clicker thing. I guess I have to restart it. All right. So if the displacement of an object x is related to the velocity according to this relationship, x equals av, then the constant has the dimension of which of the following? Let me write in some of the variables because these are sort of new to us right now. Acceleration is meters per second squared. Length is meters. Time is seconds. And area is meters squared. So what I'm asking is if I have x equals a times v, if x is in meters, a has some units that I don't know what they are, and then this is in meters per second, then what must the units of a be in order to make this expression true? What must the units of a be? Must the units of a be acceleration, meters per second squared, meters, that is length, time, or seconds, or is it area, which is meters squared? What are the units of A? Remember, you can ask your neighbor. I encourage it, actually. Just ask them what they got. It's like, well, I think that's right. They're doing pretty well right now. Almost everybody has the right answer. Feel free to ask your neighbor. In fact, everybody look to your neighbor and say, I think the answer is... All right? All right, everybody? Everybody? Okay. All right, just a few more seconds. I'm going to stop at 2 minutes. the answer is time. Mass, along with what other two quantities, make up the three basic quantities used by physicists to derive additional quantities? That is, we had mass and what and what. Remember, this was in the NKS system of the SI system. So mass, what, and what. Feel free to ask your neighbor what you put. Just a few more seconds. I'll stop at 40. Excellent. That's very good. See, when students do really well, I can tell a joke. Did I tell you the turtle snail joke? No. Okay. What did the snail say when he was on the turtle's back? What? Whee! You get it? This turtle goes a lot faster than a snail. There we go. That was just because you did so well. All right, mass, length, and time. We use those three basic quantities. Later, when we get into electricity and light, we'll see some other quantities that we use to describe charges and the brightness of light. But for right now, for a while, actually, we're just going to be mass, length, and time. And we use those quantities to derive additional quantities, like for energy and work, momentum, power, all that jazz. So, note the following expression, y equals x squared. Which of these statements is most consistent with this expression? That is, if I double y, then does x quadruple? Is y greater than x? If I double x, then does y double? And if x doubles, then does y? Which of those statements is always true? Most of you put A right now, and A is not correct. If I double y, x does not quadruple. That's not a true statement. So A is not correct. We'll encounter these types of questions as we go through. The reason is because scientists don't really think in equations so much, is that we think about how certain variables relate to other variables. So if you do something to one variable, what happens to another variable? And while the focus of this course is on the human body, the focus is also the physics of the human body and thinking about it in that way. So we want to begin thinking about, if we change one thing, how does it change another? And this is how we express that mathematically. So these type of questions are important, and as we go along, you'll get the hang of it. But right now, it's just sort of new to understand. So I'm going to stop this at 220 or 223. All right, let's see. Most of you put C. C also is not correct. Is anybody really confident on their answer? What one? What? Anybody else really confident on their answer? B is almost always correct unless x is less than 1. So like let's say x is 0.1, then y is 0.01. And in that case, y would be less than x. So that's a really great answer, and it's sometimes correct that y is greater than x. So like for example, if x is 2, then y is 4. And that certainly fills B, but it's not always that way. So the correct answer then is what? D is the right answer. Let me show you. So y equals x squared. This is the way I always like to approach these. Y is equal to x squared. If I double x, then what happens to y? That is, if I multiply x times 2, what do I have to put on the other side of the equation to still make it correct? What do I have to put in front of the y in order to make it correct? The 4, right. So, because over here, I multiplied x by 2, I have 2 squared, and 2 squared is 4, so I have to increase y by a factor of 4. So if x doubles, then y quadruples. Y'all are sort of thinking that when you put a, but you got it flipped, right? It's not if y doubles and x quadruples, it's the other way around. All right, can y'all see the red? Sort of, not really. I'll use a darker color for that. All right, since 1967, the standard definition for the second of time is based on which of these? The frequency of the cesium atom, the average solar day, the sidereal day, or Greenwich simple time. We already have this question. I just want to, while you put in your answers, the answer is not B, but the answer used to be B. The standard for time used to be based on the average solar day. Did y'all know that? People used to base their time on the length of the day, the second of time. I mean, of course, in ancient times, everybody based their standard of time in their minds on the length of the day. But in more scientific, since the scientific revolution, they also based the second on the length of this day, which is not a very good standard, even though it's accessible to everyone. It sort of changes throughout the year, right? I'm going to stop this at 1 minute. Since 1983, the standard meter has been defined in which of the following? By which of the following? So which of these is this current standard for the meter? A bar in France, wavelength of light of krypton, the distance from the Earth's equator to the North Pole, or the distance that light travels in a certain amount of time? Feel free to look back at your notes. If you think you know the answer, please tell those around you or share it with them. I'm going to stop at 50 seconds. 50 seconds. D is very good, that's right. Used to be a bar in France, but since then, you know, the bar in France is not a very good standard because we have two attributes of a standard. What are they? They're what? Accessible and unchanging. They also have to be accurate as well, but accessible and unchanging. And the bar in France was neither accessible nor unchanging. Just like how the kilogram is a certain cylinder in France, it's not accessible and it's also changing with time. The bar in France was not a very good standard for a similar reason. And since we've gone to the distance that light travels in a certain amount of time. And this is accessible to everyone. It's very simple to measure the speed of light. And when you know the speed of light, you know what a meter is. Like an undergraduate student can measure the speed of light. You just need a mirror on a little motor spinning, and you can measure the speed of light pretty easily. The meter used to be based on the distance from the Earth's equator to the North Pole a long time ago, prior to when it was that bar in France. So we're going to skip this right now. The speed of a boat is given in knots. If 5 knots were expressed in the SI system, then the units would be what? The speed of a boat is given in knots, but if you express that in the SI system, you convert the units into the SI system, what would it be given as? The speed of a boat. to stop at 50 seconds. 50 seconds. They're doing pretty well. Almost everybody has the right answer. Excellent. Meters per second. Distance per time. Distance is meters, time is seconds. I'm going to do this one, but I'm gonna do it with you, so I'm going to help you with it. Because I think the dimensional analysis is still, it's a little shaky for y'all, just a little bit. I'm going to help you with this one. You'll have one or two questions on your exam, but they'll be a lot simpler, all right, than the ones that than some of the ones that we see here. So let's say that we have t equals x over v. If it's dimensionally correct, that means that the units on one side are equal to the units on the other side. So, for example, on the left-hand side, I have what units? Just seconds. I have seconds. And then x is what? Meters. And then I have v, which is meters per second. Can you tell me if that's dimensionally correct or not? Let me show you how I'm going to write this. I'm going to write it a little bit differently. Because when I have things in the denominator, when I bring them up into the numerator, I flip them. So I can write this exactly the same. Seconds is the same. I have meters, and then I can say seconds over meters. So I have this fraction in the denominator. When I bring it up into the numerator, I flip it. Coming back to you a little bit, maybe? All right, so when I flip this, my m's cancel. Is this dimensionally correct, this expression? Yeah. Often physicists, they'll just sort of look at equations and say, well, the dimensions add up. And if they do, then they assume that, well, that must be right. It might not always work, but it works a lot of the time. All right, so that one is okay, so that's not the answer. Now let's do B. I have meters per second squared equals meters squared per second squared times 1 over meters. What I've done is x is meters, but it's in the denominator, so I've just written it as 1 over meters. But often it's a lot easier to see it that way. Is that dimensionally correct or not? Are those units consistent? Yes, no? Yes, they are, right? Because if I cancel out a meters here with a meters here, I'm left with 1 in the numerator, meters per second squared. So that one's not the right answer. I'll let y'all try C. You tell me if it's correct or not. V is meters per second, A is meters per second squared, and T is seconds. Is it dimensionally correct? What do y'all think? Yes, raise your hand. No, raise your hand. Okay. No is correct. So V is meters per second. A is meters per second squared. And T is 1 over seconds. Or excuse me, 1 over T is 1 over seconds. So here I have meters per second, and over here I have what? Meters per second cubed, right? Second squared times second. So that one is not correct, and so C then is our right answer. Because it's asking for which one is not dimensionally correct. I'm going to show you this last one. This last one's probably a little bit more complicated than you might have on your exam coming up in a few weeks. But let me show it to you nonetheless. So second squared. Anytime I have a constant like this, I just forget about it. I don't do anything with it. I just leave it out completely. So second squared meters, second squared over meters. Oh, excuse me, second squared over meters. Those cancel, and so that one is dimensionally correct. All right, so on the exam, you'll see a few questions about standards, and you'll see a few questions about dimensional analysis. And then like we did last time, you'll also have to do some simple unit comparisons. Okay? So you should be up on those three things. Now, right? No. Now I can help you go back through the examples. I don't usually give homework. We do a lot of examples in class, but if you feel that you need some extra problems just to practice, just let me know. I can throw it together or something. Alright, so if you feel like you need help with dimensional analysis, go back and look at the notes or the examples we did. I'll post these examples online, so you can look at them. And you can also look back at the old exams and look at sample problems there. They're linked from the website to get an idea of what kind of questions I'll ask on the exam. And if you still feel like you're just not getting it, then please shoot me an email, come see me, call me, talk to me, whatever you need to do to get the help that you need. It's my job to help you do well in this class, okay? Let me do that job. All right. We're gonna move. No, let me stop this. Everybody clicked in, okay? C is the right answer here. Not everybody has, I don't think. I'm gonna take it away at 540. 540. I will post this on the website. Let me just remind you on that website these resources that I've told you about. Really quickly. Hey, that's my wife. And that's my little girl. She's a lot older now. She's sick, by the way, at home. I'm not going to be in this afternoon. She's been sick for like 2 days, so I have to go home and take care of her this afternoon. So if you go to the website, you can find old quizzes and exams here. So for example, if you look back at spring 2014, for example, here's one about dimensional analysis. You can take a look at that and look at some of the various problems that are related to that. And then I also have spring 2013 as well. For spring 2013, I actually have video solutions to them. All right, so you can take a look at that. Though in 2013, that might not be terribly helpful for you because we used a different book then. I just sort of ran the course differently. So you can take a look at it and see what you think. If you have questions about them, let me know. Okay, there's a quiz on Thursday. That quiz is going to be a reading quiz. If you've read the chapter, I might read it through twice maybe, or if you're a careful reader, once should be fine. And I'll pick out some of the main ideas from that chapter. And there'll be 10 multiple choice questions. It'll be pretty quick quiz. You'll probably only get like 10 or 15 minutes at the end of class to take it. And that's it. Remember, guys, I guarantee you at least how many quizzes? 6. I count 5. Likely we'll get 7 or maybe even 8 quizzes. Sometimes it's hard to get 8 quizzes, but I guarantee you 6. There is a drop quiz in there. Probably two drop quizzes. But really chopping pretty well, we'll get 3, but probably not 3, but probably 2. And that quiz will be on chapter 1. Stuff that we haven't covered yet, that we might get to a little bit today, but just strictly from the chapter. All right, first I want to define a couple of things because we're going to talk about them in that first chapter, having to do with kinematics. We have a couple of different quantities, what we use when we talk about kinematics. Kinematics is just the study of motion, right? Same word as like kinesiology, the study of motion, or the physiology of motion. Kinematics. We use 3 different expressions. That is distance. You might also hear this called displacement. Those are very similar quantities. They're a little bit different, but they're very similar. We use velocity or speed. And then also acceleration. And then we can describe these pretty simply as just how far something has gone, how fast something goes, and then how fast something speeds up. Or how fast it slows down. Alright, so distance then is measured in meters, velocity is measured in meters per second, and then acceleration is measured in meters per second squared. That is meters per second per second. So for example, if something is accelerating at, I don't know, 10 meters per second squared, how long does it take to get to 30 meters per second? It's accelerating at 10 meters per second squared. How long does it take to get to 30 meters per second? It's accelerating at a rate, that is, it speeds up at 10 meters per second per second. How many seconds does it take then for it to get up to 30 meters per second? What does it mean to go at 10 meters per second per second? So how long does it take to get up to a speed of 30 meters per second? 3 seconds. Because in the first second, you accelerate at a rate of 10 meters per second. After 1 second, you're going how fast? 10 meters per second. After 2 seconds, you're going an extra 10 meters per second, 20 meters per second. And then after 3 seconds, you're going 30 meters per second. Right, so that's what our acceleration means. We're going to deal with this in relation to forces and what have you. But I want to introduce them here. I'm going to do a quick activity too. Do you all have cell phones on there? If you have a cell phone, I'm going to need about 4 or 5 people. We're going to measure the speed of this thing. This is a little car. It's a constant velocity car. And we're just going to measure its distance that it travels. We're going to measure the distance that it travels, and then we'll find the time that it travels, and we can take the quotient of those, divide the two, and we can find how fast it's going. What is the velocity? Probably about 4 people with cell phones. They have little timers on them, like smartphones. Let me get it up here. Ron, you gonna help? Who else? Emily? All right, Ron, you will, and then not even one person without a phone. Yeah, so 2 you ladies come on up, and then one more person. Not everybody at once. All right, Josh? Let's see, I think that should be good. All right, now let's see. Emily, why don't you stand here? And, Noah, you stand here. Let's get one more person. Janelle, all right, Juana, you want to help? So you're going to stand on these lines right here. And what you're going to do is you're going to time this when it passes your line. Juana, why don't you go there. You come down here, Emily. You go there. And Josh, you can, or no, you right there. And Josh, you right there. Okay, so what we're going to do is, I don't think you're going to need your phone actually. You're just going to, all right, you're going to sort of keep this on track. Okay, so as it goes along, you need to make sure that it goes in a straight line. And then y'all are going to measure the time. So for example, Ron is going to let it go right here, and then it's going to travel along. Everybody's going to start their timer when he says go, and the car starts. All right?
Like kick it over?
No, I'll turn it on. Oh, right, yeah, you turn it on.
I'm saying to keep it straight.
Yeah, you just sort of, like curling, right? So when it gets to you, you stop. When it gets to you, you stop. You have your phone on? Noel, when it gets to you, you stop. And then Josh, when it gets to you, you stop. All right, so no, you do need a phone. I'm sorry. Yes. All right. Is this clear? So what you're going to get is you're going to get times up per distance. So you're going to have the time that it took to go 1 meter. These squares are about a meter. Actually, they're about a yard. And then you'll get it for 2 meters, 3 meters, and 4 meters. All right, you ready?
You don't get a squeaky?
You don't get a squeaky. You just use your hands or your feet or whatever. Because it'll sort of, it doesn't go in the perfectly straight line. All right, you want to let it go? And then just tell them to start whenever you let it go. You stop, Luana. Alright, you can turn it off. Fine. Y'all keep those times.
I'm gonna set it.
Oh! Alright, can you do it again? It's okay. Everybody messes up sometimes.
1.
Alright. So, Emily, what do you have for time?
1.8.
1.9 seconds. Who's the next one?
3.43.
3.43. 6.1. And 7 point what?
7.
Okay, I'll just call it 7.7. Alright, so you were at 1 meter, 2 meters, 3 meters, and 4 meters. Y'all can have your seat now. Thank you. Alright, so what we have here is the distance versus the time. So I can find what is the velocity of this. I can say it took 1.9 seconds to get there, divide the two, and I'll find the velocity. So I just say this divided by this. It tells me it's going about a half a meter per second. All right. Or similarly, I can do the same for the others. All right, and they all come up about a half a meter per second. There's some uncertainty because, Ron said to push start, and maybe you didn't push start right away, or maybe it wasn't going in exactly a straight line. But you see, you get pretty good calculations, about a half a meter per second for all of them. So it takes that little car about a second to go a half a meter. So a second to go roughly from here to here. Let me show you something else that you can do with this that we often do. We're not going to do much graphing, but I just want to show you nonetheless. Let's see. Insert chart. Y'all use Excel much? No? Okay, that's okay. Alright, so here I have a chart. Did I get this right? Yeah. I have a chart. On this axis I have the distance, and then on this axis I have the time. And notice, what kind of line is that? Is it a curved line or a straight line? It's pretty darn straight, right? Because this type of relationship versus distance versus time is a linear relationship. That means as you change time by a certain amount, say by a factor of 2, the distance changes by the same amount. If I double the time, I double the distance. I can do something else here. I can fit it with a line. Add a trend line. Even in allied health, there's actually a lot of applications for this, for doing various calculations. Let's see. And I find here an equation that fits that line. And notice this number, you might not be able to see it very well, but this number represents the slope of that line, the rise over the run of the line. Remember slope? It's 0.51, which is awfully darn close to our values that we measured over there. So you can find the velocity of something by graphing its position versus its time, and then just finding the slope of that. That's pretty interesting. I didn't know that. That's what you were supposed to say. Or maybe you did know it. All right. All right. Let's look now. We're moving sort of into Chapter 1. Chapter 1 deals with a lot of stuff, all right? So we're going to cover what we would normally cover in about, I don't know, 2/3 of a semester just in Chapter 1. Basically all of classical mechanics, kinematics, forces, Newton's laws. We'll look at torques. I think we also do energy and power. Oh, no, that's a later chapter. We'll do rotational motion and what have you. So a lot of good stuff there that applies to the body, and just a lot of physics as well. We're going to look at Newton's laws. First of all, Isaac Newton. You've heard of Isaac Newton? He did a lot of stuff. He really changed your life in a lot of ways that you're probably not aware of. primarily, he's famous for what? Isaac Newton, famous for. How do you know him? Probably for his laws of motion, right? Is that correct? So at least heard of them, I think. You know, F equals ma, action, reaction forces, those sorts of things. But really, what he did to change your life, literally changed your life back in the 1600s, about 1660s or so, is he invented something. He invented the study of calculus. And the study of calculus really changed your life because it allows for things like this building, the construction of large buildings, for the creation of cell phones, for the creation of computers. Calculus basically is a bedrock for a lot of what we do in science, and a bedrock then for a lot of the advances that we've made in technology, medical technology, communications, what have you. So the laws of motion are great, but really it was his invention of calculus which led him to these laws of motion that really changed the way we live today. All right, so Newton's laws of motion. We're going to watch a video here in just a minute, but first let me just sort of give you a little primer. The first law is inertia. There are three laws. The first is called the law of inertia. Remember the video we watched on the first day? Richard Feynman, his dad described to him what inertia was. Right? Do y'all remember what he said? Right. Inertia is what we use to describe the ball going to the back of the wagon. Inertia is the tendency of an object to stay in its current state of motion. All right, so the ball moving to the back of the wagon, if you have a wagon that you pull, the ball is at rest before you pull the wagon, and then as you pull the wagon, why does the ball move to the back of the wagon in terms of inertia? Okay, yeah, forces, well, no, not because of forces. It's trying to stay in the same spot. It wants to stay still because it is still. And so when you pull the wagon, you're trying to move it, but it says, no, I have inertia. I want to stay right where I am. Okay. This also applies for objects that are moving. If I have an object that's rolling along the floor, it wants to continue in that state of motion forever. And so that will actually occur if you have an object that's rolling along the floor. If there are no other forces acting upon it, it'll continue in that direction until forever, until it runs into the wall. Okay? So this measure of inertia is just a tendency of an object to stay in its current state of motion. And Feynman's right, we don't really understand why this is, but we observe it to be true. And Isaac Newton observed it to be true as well. Inertia we measure with the mass. So if we have an object with just a little bit of mass, then we say that object doesn't have a lot of inertia. If we have an object with a lot of mass, we say, well, that object has a lot of inertia. So inertia is simply measured by mass. All right, so who has more inertia, me or my little girl Ada? You. I have a lot more inertia than she does. As a result, it's going to be a lot harder to get me to move than it is to get her to move. Like you just sort of push her a little bit and she'll fall over. But if you push me, it's a lot harder to get me to move. Bigger things are harder to move because they have more inertia. All right. The second law of motion is the law of acceleration. In equation form, Newton said it this way. He said that the acceleration is equal to the force divided by the measure of inertia, which is the mass. Right. Said if you had a big force, then that gave you a big acceleration. And if you had a big mass, then that gave you a smaller acceleration. We usually see this in another form, and that is just say F equals ma, where instead of solving that for F, we solve it rather instead of solving it for A, we solve it for F. Okay, so these are the same. I just took this equation and multiplied both sides by n, and then it became this. All right, so that's Newton's second law. If I apply a force to a certain mass, I accelerate it. I cause it to speed up at a certain rate. That's Newton's second law of motion. And then finally, the third law was the, what do we call it? The law of reaction. So the law of inertia, the law of acceleration, and the law of reaction. It says every force has an equal and opposite force. Every force has an equal and opposite force. Maybe you need another minute to let that sink in. Because you aren't showing like the level of excitement that I would expect you to show. That means that anytime you have a force, there has to be another force that's equal and opposite. All right, so for example, I don't know, I hit this board. What is the other force? I obviously feel a force in my fist. I hit it with my fist. What's the other force? The wall, right? The wall pushed back on my fist, right? Or you get into a fist fight, right? Anybody ever been in a fist fight? One time when I was in, what was I, 6th grade, 7th grade, Nelson Zamora, anybody know Nelson Zamora? We got into a fist fight. I forget what it was about, but it was very stereotypical. It's like, we're going to meet after school. When we did, we met after school in the field away from school, and we got to a fight, and then I don't think anybody really won. We both were sort of all black-eyed, bloody noses, but nobody else was there to watch us either. It was just the two of us. But anytime you hit something, you're going to feel an opposite force that's in the same direction, right? We're also going to talk a little bit later about field forces. That is, forces like the gravitational force. There's a force between the Earth and the Moon in the same way that there's a force between me and the Earth. Right, so how the heck then can I have a field force, that is a force between the Earth and the Moon that doesn't require contact? How can I have that force and then still have an equal and opposite force? So the Earth pulls on the Moon. What is the other force? You mean what? Okay, very close. What can you explain to me about pulling away? Okay, close, but not exactly. Huh? The moon is pulling the Earth. So I have the Earth, that might have been what you meant, I'm not sure. But you have the Earth and the Moon. The Earth is pulling on the Moon, and in a similar way, the Moon is pulling on the Earth. Or I can think about it this way. The Earth is pulling on me. You might know what my weight is in newtons, which is our thing for weight. About 700 newtons. It's useful to know your weight in newtons, I think, so that like your friends can impress you, or you can impress your friends. Hey, I'm 500 newtons, or I'm 1,000 newtons, or whatever. I'm about 700 newtons. Typical person about 700 newtons. So the Earth is pulling down on me with 700 newtons of force. Likewise, I'm pulling back on the Earth with 700 newtons of force. Anytime you have one force, you have to have a second force that's equal and opposite. And that was kind of groundbreaking for his day. All right. In fact, all of these things were a lot different from the way people thought. And actually, these three laws, like you might think, yeah, but out in real life, as you go about walking around, you probably don't really apply these laws in the correct way. In fact, the way that you think is probably a lot different than the actual way of reality. I have a little video here. This is a Veritasium video. It's that same guy, that Australian dude that I showed you last time with the sphere. He has a whole string of videos that are really great. So I'm going to show you another video where he talks about the laws of motion, but the incorrect laws of motion. A lot of these were ways that Aristotle thought about motion, and Newton really came along and he changed the way people thought about motion. It was a paradigm shift. Y'all heard that term, paradigm shift? where the way that we think about something as a society changes. And he really did that for motion, because prior to this, people thought about motion very much in the way this video talks about. So we're going to watch this little video. It's just 4 or 5 minutes long, I think. All right, so we have lots of different types of forces. Your book goes through these, and they sort of have like a section on each one. One type of force is weight. Weight is the force of gravity. On an object. So for example, I have a certain mass. All right, my mass is about 70 kilograms. But that's a different thing from a force. A force is a mass is a measure of inertia. It's a measure of how much material is in your body. But a force, and this is the force due to weight by Newton's second law, is that mass times some acceleration. Right? And that acceleration that we have on Earth is about 10 meters per second squared. So my weight then, which is different from my mass, is going to be 70 kilograms times the acceleration due to gravity on the Earth are about 700 newtons. The unit for weight, or force, is the newton. Of course, after Isaac Newton. By the way, just if you're a grammatical kind of person, whenever you're writing units, if it's named after a person, you always abbreviate, or you always capitalize the abbreviation, but you don't capitalize the word when you write it out as a unit. You capitalize, of course, the person's name when you write it as their name, but not the word. So if you care. I'm the kind of person that cares. So. Do you care? Not really. Yeah. Okay. All right. So that's going to be my weight. Remember, this is different from mass, because mass is a measure of inertia. Mass is a measure of how much material you have within you. We just have a few more minutes. Y'all hang on. I know it's getting long. It's a long class period. I have another video. Is that okay? Want to watch another video? This one is also this Veritasium. I'll show you different types of videos as we go along. But in this video, he talks about the difference between mass and weight. I think I have it here. Yeah, here we go. It looks like it's a little bit longer. And a couple of different points that he talked about there that you should be aware of. The car is difficult to push because why? Why is the car difficult to push? In fact, it's actually not that hard to push, but why was it difficult to push? Not because of the force of gravity, because of the inertia. Bigger things are harder to put into motion, right? Now, if you were trying to lift the car, then it would be hard because of the weight, right? So if you're trying to push it up, it's going to be very difficult to lift. But if you're just trying to push it in a straight line on a flat surface, then it's because of the inertia, right? That's this sort of innate tendency that we don't fully understand why it is the way that it is, but this innate tendency for an object to stay in its current state. All right. Now, I like to do what? What's the thing that I like to do? What was in my knee bag? I like to cycle, right? And so cyclists spend thousands of dollars. I don't, because I'm kind of poor, but I'm not that poor. But cyclists spend thousands of dollars to get bikes that are what? Like really, really light. Like they make them out of carbon, they make them out of aluminum. These materials are titanium. They make them out of materials that are strong yet very, very light. Right? But around here, especially around here, because the ground is very level, it doesn't really matter. Because once you get a bike up to a certain speed, once you overcome that inertia, it doesn't matter how heavy your bike is. Right? Your bike can be 5 pounds or it can be 50 pounds. Once you get it up to a certain speed, it doesn't really matter how heavy it is. Because it doesn't matter about the weight. The weight is down. You're going in this direction. So it doesn't matter about the weight at all. Now, fancy bikes are fancy for other reasons too, right? They have great components and the components have less friction within them. So I'm not saying that people that spend thousands of dollars bikes are crazy. Maybe they're a little bit crazy. Are there any people that cycle? No. Okay, good. So, so anyway, the point is that the weight doesn't really matter when you're just going into a straight line. All right. Let me do one more type of force, and then I know y'all are ready to go, but give me just a couple more minutes. All right. Another type of force is a normal force. Normal is a mathematical term, and it just means perpendicular. So a normal force is a force in response to another force that is perpendicular to the surface. So for example, if I have a table and I have a block on it, it has a certain weight, and that weight I'm going to represent with an arrow. So this arrow represents the force weight. The normal force is going to be a force that is perpendicular to the surface of the table. In this case, actually, the normal force is equal to, less than, or greater than the weight. It's equal to. That's an application of Newton's third law, right? That the normal force equals the weight. That's my action-reaction pair of forces. This is third law. All right, let's say instead I had a block sitting on a wedge, or an inclined plane we call it. All right, now here my weight would be down. What would be the direction of my normal force? Would it be up to the side? What would it be? How do you think? Tape? Is it tape? Like this? Would it be like that? Would it be like that? Would it be like that? Yeah. This is the force that is the normal force. So my normal force then, you see how it's perpendicular to the surface. It's at an angle of 90 degrees to the surface. It looks like this. Right? The normal force is always perpendicular to the surface. We'll deal with this in a little bit in a later class. All right? Can I borrow somebody's book right quick? A quick primer on the quiz, which is on Thursday at the end of class. It'll just be on chapter 1. All right, so for example, I'm just going to read through the chapter and I'll pull out things. And so for example, I'll try to make them big ideas, not just minutia. But here it says Newton's second law can be written mathematically as, and I'll give you a few equations and ask you to pick out the one. That's straight from the book. Or I might say, then I might just use this book because it has all the main ideas highlighted. It says right here, friction is a force that opposes the motion. I might use that. Friction is a force that does what? Does it oppose the motion? Does it produce motion in the forward direction? Something like that. It'll be straight from the book, and I'll try to pick big ideas. So, don't focus on the minutia. Also, in the second part of this chapter, it talks about the human body, and I'll also ask questions about that. The different joints, the different muscles, the skeletal muscles, the smooth muscles. Y'all know all that stuff, right? The human anatomy. And most of you already have that. You understand what the quiz is? Same question before we maybe you fill in the blank. It'll be at the end of class. Have a good day, okay? Run.